everyone. Welcome back to the Mobile Robot Systems course. This lecture is all about methods that allow us to plan paths for multiple robots sharing the same workspace. So it extends some of the notions that you've learned about in the prior lecture on single robot path planning. Here, though, we will be making a clear distinction between methods that plan in the discrete domain, where robots move essentially stepwise on grids, and those that plan in the continuous domain, for example, for velocity-controlled robots. I'll be showing you a couple of cool movies too, so stay tuned for that. Without further ado, let's get started. So in this lecture, we'll be talking about multi-robot and multi-agent path planning. And I will be starting out by giving you an overview of the taxonomy that we use to refer to the various classes of multi-robot path planning problems. And then we'll go in and talk about two different domains within the field of path planning. One is commonly referred to as multi-agent path planning, which deals with the problem in the discrete domain. And the other domain we'll be talking about is the class of solutions that solve the path planning problem in the continuous domain. And at the end, I will be concluding with a couple of examples of how we can actually solve the concurrent assignment and path planning problem. To set the tone for this lecture, I'd like to start off by showing you a movie that illustrates an example of multi-robot path planning. So what you see here in this movie is a couple hundred epoch robots. The epoch robots are relatively small robots. You can hold one in your hand. And you can see them going about a task here. And I'd just like you to watch this movie, and I will ask you a couple of questions at the end of it. So what you saw these robots do here was navigate together in a shared workspace to, in this particular case, aggregate into the logo of the school where it was filmed, the EPFL. Now, as you saw, these robots, they all navigated without colliding, and they all went to predefined locations in space. So I'm just going to play this movie again, whilst I now let you think about how this was actually achieved. So clearly, it seems like every single robot knows exactly where it's heading, and at the same time, the robots seem to be circumnavigating each other in an extremely efficient way without big detours. Now, for those of you who have already figured out what the potential solution is, let me give it away. In this particular case, well, this was actually filmed a couple of years back. I was just starting my PhD at EPFL, and it turns out that at the time we didn't really have really efficient multi-robot path planning solutions available to us. And so what really happened in this movie is we actually filmed the robots starting out at the locations of the EPFL logo, and the movie that you're seeing here is being played in reverse. So, and I was at the time one of the PhD students, or one of the volunteers that was running around catching the robots and bringing them back to their initial origin spots at their designated locations within this logo image. That was a lot of fun, but the reason I'm showing you this movie is just to show you how hard it actually is to design an algorithm or develop a method that actually solves the path planning problem for very large robot systems, so that they can actually achieve their goals or reach their labeled or designation locations effectively without collisions, and also quickly in time without going about large detours. And to this date, this multi-robot path planning problem is one of the most active research areas in the area of multi-robot or multi-agent research. So as I promised, we will be going through a couple of terms here in order to give you the tools to refer to the various classes of methods within this research domain or application domain. So one very important distinction we make is whether or not we're planning in the continuous domain or the discrete domains. So in the continuous domain, we typically talk about planning time parameterized trajectories in metric space. Whereas when we're solving the planning problem in the discrete domain, we're talking about planning on graphs or discretized spaces such as regular grids. Now, when we plan a path for a robot, most cases, we're assuming that this robot has a designated goal location. So a specific robot ID has an allocated location in space. That particular type of problem is referred to as a labeled planning problem. So each robot has a predetermined goal destination. Unlabeled problems also exist, where you can start off with a multi-robot system and you have certain goal locations that need to be reached, but it doesn't matter which robot reaches them as long as they are reached by someone, right? The problem representation can be either coupled or decoupled. And this is very important in terms of understanding what the complexity is of the solution that you're deploying, as well as what guarantees it's providing you. So coupled solutions tend to represent the joint state space of all robots in the system, whereas decoupled solutions model each robot state independently. And there are consequences that we will talk about when choosing either coupled or decoupled planning methods. And finally, planning can be reactive or deliberative. So in the reactive sense, we're really thinking of robots reacting in the more short-term time horizon, where potentially they're just reacting to obstacles that they encounter along their way. And they're really planning as they go, with rather myopic views of how they're going to be going about their final tasks. In deliberative planning, we're really planning for optimality, so we have an optimization objective that often considers the problem to completion, so until every single goal has been achieved, or every single robot has reached their designated labeled locations. And these kinds of deliberative planning approaches usually can only be modeled when we think of their systems as centralized systems, and we're modeling the state spaces in a coupled representation. And finally, computation can be executed either locally on each robot independently, so in a decentralized manner, or we can do this in a centralized manner. Right. So first, let's abstract away all the elements that make planning difficult for robots. And let's talk about the simplest possible way of thinking about planning in the discrete domain. So we're going to start by looking at discrete domain path planning for multi-robot systems. And in this particular case, what we also do is we actually refer to the problem as a multi-agent path planning problem, because we're also abstracting the robots to the extent that they're really just point robots, and people in literature actually refer to this as a multi-agent problem. Okay? So the first thing that we do is we discretize our environment. So we're considering grids or planar graphs. And our robots are no longer motion-constrained robots, but they're now point robots that are holonomic and can move from one given grid cell into another without being constrained in any way. Now, the problem that we're trying to solve is, well, we're given a number of agents that are at known start locations, and these agents have predefined goal locations in a known environment. So we know where the obstacles are in this environment, and we know how it's bounded. So what these agents are trying to solve here is they're trying to find collision-free paths that lead them from their start positions to their goal locations, such that they're optimizing some higher-order optimization objective. Okay? And we'll talk a little bit more about this in just a second. So as you've inferred from this problem description, the multi-agent path planning problem is generally a labeled problem. So we have designated goal locations. And this applies really well to a lot of different problems that are relevant to date, such as logistics, as is seen in automated warehouses, for example. So let's talk a little bit more about how we're representing or how we're modeling this multi-agent path planning problem. So these point robots that we're now moving on our grids or our discretized spaces can move in 4 different directions. So they can move up, down, left, or right. And what's important here is that we want to avoid these robots from colliding. So how do we model collisions now that we're already abstracting motion away to such simplified notions? So collisions can happen in two different cases. So we can either collide when two robots move into the same cell. We call this kind of collision a vertex collision. Or the robots can collide when they are swapping cells, essentially using the same edge, or the same road, essentially. In this case, we call this an edge collision. Now, if we have robots that are simply swapping cells and moving in rotation, such as depicted in the third panel on this slide, we don't actually incur any collisions. So I mentioned something about performance before, optimization objectives. And generally, in multi-agent path planning problems, there are two relevant optimization objectives we might want to consider, or two different ways of measuring the performance of a multi-agent system. The first is by considering the make span, which simply counts the time it takes for the slowest robot to reach its goal, right? So this is measured by the time of the last robot's arrival at its designated goal location. And the flow time is simply the sum of all robots' arrival times. So in a system of n robots, you'd simply be summing up the travel time over all these n robots. So make span and flow time are the two classical performance metrics we generally use to refer to the performance of multi-agent path planning solutions. So I mentioned the taxonomy of coupled versus decoupled path planning solutions. And I want to just illustrate why this distinction is actually important and what consequences it has for the solutions you'd be deploying. So let's have a look at the example that I'm showing you here on the left, where we're considering, let's consider a decoupled solution, right? Which essentially means the robots are going to be planning independently. Now, in this decoupled solution, what would happen is potentially both robots start moving simultaneously, or the green robot perhaps starts to move first and tries to reach its goal. So in this particular case, if green moves first and stays put at its goal location, there is no way that the blue robot is actually going to be able to reach its goal, and we have a deadlock situation. Now, on the right-hand side, I'm showing you an example of a coupled system where the green and blue robots are modeled as a joint multi-robot system, and planning here takes into account the paths that both robots would have to execute to reach their goals. So in a coupled scenario, the blue robot would move first and would then move to its goal, such that it is impossible for it to get into a deadlock situation, given the path that the green robot needs to follow to reach its own goal, right? So in the left-hand scenario, we have a potential deadlock, and in the right-hand scenario, if we plan such that the blue robot goes first, we are able to achieve completeness. In other words, all robots will eventually reach their goals, okay? So to summarize, coupled planning approaches provide completeness, and decoupled planning approaches do not necessarily provide completeness. Okay? So because of this, these two approaches towards planning problems are tackled in different ways, and we'll be looking at a couple of solutions for both of these different classes. But first of all, I just want to highlight one thing, right? So if we state, or if our premise is that coupled planning is definitely the more powerful way to solve planning problems, then why don't we just consider coupled planning and reject all solutions that model systems in an independent way in decoupled representations? So the answer to this question actually lies in the complexity of the methods. And I'd like to go into a little bit more detail to really convince you of this juxtaposition by working through the example on hand of a multi-robot path planning problem. Okay? So we'll start by formalizing the problem. So let's assume that robot I has a configuration space, C sub I, and a joint state space then, when multiple robots share their workspaces, is then given by the Cartesian product of all n robots in a system, such that I have this joint state space X, right? And it's simply the concatenation of these various configuration spaces. So note that the dimensionality of a problem grows linearly with respect to the number of robots in this case, right? Because we're concatenating the various configuration spaces. And as we've already established, we know that algorithms such as A* require time that is at least exponential with respect to the search space dimension. So let's work this out on for the specific case of path planning for robots that work in discretized domains. So let's consider a system that is composed of n robots, and they operate in a world that is discretized into m cells, so m various states that are possible for the robots to be in, which means simply that a robot here lives in an m-dimensional state space, okay? And hence, a coupled representation in this case would need to consider a total of m to the power of n states for this joint multi-robot system, right? So if we were now to use an algorithm such as A*, what would it mean for the complexity of computing a solution to this coupled problem? Well, basically, we know that the worst case complexity for A* is in the order of the number of edges, which is approximately in the order of the number of vertices, in the case that we know we have a graph that is sparse, which in this case is equivalent to m to the power of n, right? And so what we can derive from this is that computing solutions for these multi-agent planning problems has an exponential complexity in the number of agents that we're including in these systems. Okay? And so clearly this becomes intractable very quickly as we increase the number of agents for which we're trying to plan solutions. So I'd just like to summarize a couple of facts about the coupled path planning problem. So first of all, it has been shown quite recently actually, or proven, that it is NP-hard to solve for optimality for either one of the two objectives that I introduced before. So either makespan or flow time, right? And we also know that it is impossible to minimize or to optimize for both of these objectives simultaneously, because we have a Pareto front that we need to consider that is given to us as we try to optimize for makespan versus flow time. Yet on the other hand side, we also know that the coupled methods provide us completeness as well as optimality. And this is actually the main reason why we're so keen on deploying solutions that have been solved through coupled planners. Yet the intractability is a problem, and because of that, lots of attention has been devoted to this field, and it is a very active research area. And because of this, there is still an ongoing thrust where approximate solutions are being proposed. And I encourage those of you who are interested to look deeper into this by looking at papers and literature by a few of these authors that I have noted here, as well as others that you will be able to find through following these links. Okay. So there are ways of achieving completeness in planning approaches that are actually decoupled. And I just want to introduce one of the possible ways of doing this. So as you recall, we showed in that little convincing example that if you're looking at a warehouse environment or some sort of workspace that is represented as the one here in these two panels, then if we don't plan in a coupled way, we might end up in the situation where we have deadlocks and we don't achieve completeness. So there is a way of actually building or designing your workspaces such that robots or robot systems can achieve completeness. And we generally refer to these kinds of environments as well-formed environments. And the solution by which we then plan the paths for the various robots in a decoupled manner is prioritized or prioritization. So what is a well-formed environment? Well, essentially a well-formed environment is just an environment that makes sure that robots' endpoints are distributed in such a way that any robot standing on an endpoint cannot completely prevent any other robots from moving between their endpoints, right? Start and endpoints. So in other words, in a well-formed infrastructure or workspace, A robot is always able to find a collision-free trajectory to any other unoccupied endpoint by simply waiting for the other robots to reach their destination endpoints, and then by following a path around those occupied endpoints, which in a well-formed infrastructure is guaranteed to exist. Okay? So that's basically the meaning of a well-formed environment. So just a little bit more formally, so a summary of the conditions. In a well-formed environment, there must exist a path between any two endpoints, right? That path must have at least R clearance with respect to static obstacles and at least 2 R clearance to any other endpoint. And we're assuming here that R is an approximation of the robot's radius, or how much space the robot uses. And hence the robot is always able to find a collision-free trajectory to its goal, right? And the way it does this is either by waiting for other robots to reach their goal first, and then following a path around those occupied goals, or it's the one that's being prioritized and it directly moves to its goal, right? And the key thing here is that any prioritization in the multi-robot system works. And that is why this uncoupling leads to completeness for well-formed environments. So let's talk a little bit about decoupled systems. So if we decouple the problem, what does it mean for a robot? Well, essentially it just means that every robot or agent can now plan in its own space-time, right? So it's no longer a joint space-time problem, but an independent one. And because every robot is now planning independently, when robots encounter potential conflict zones or collisions, impending collisions, they need to negotiate which robot can actually go first, right? So this is an ad hoc prioritization that would have to take place in the case of an oncoming collision. And further to this, we can actually deconflict robots online. So as the collisions and conflicts appear to be arising, or we can solve this completely offline a priori before the robots start moving. So if we look at this example here, we can assume that the green and the blue robots can talk to each other given a certain visibility range or a communication range. And when they're within range, they say, oh, I'm actually going this way. And the other robot says, I'm also going that way. But we're both in our space-time plans, we're both going to be occupying this very same cell at the very same time. And hence we need to deconflict these space-time path plans, right? And that's what they then do, and they prioritize, and after they have done negotiating, one robot will go first and the other robot will then follow. So this is simply the mechanism by which decoupled path planning would work in an online deconfliction planning method or planning solution. I can also represent this with space-time graphs in a slightly more sophisticated example. So here we are assuming we have 2 different robots of different size. So I have a red robot, a small robot that starts in the left bottom hand side corner of the left panel. And I have a big robot, blue one, that starts in the right hand side corner of this panel. And the red robot wants to move into the upper right hand side to its goal position, and the blue robot wants to move through this corridor to the left bottom hand side. Now they can't do this at the same time because the blue robot consumes a lot of the space of this corridor and would collide with the red robot whilst doing so, and vice versa. Okay? So those 2 trajectories that I've plotted out are the ideal trajectories for these robots, and in this particular case there is no other way of getting there because the workspace is constrained. Okay? Now if we look at a potential decoupled solution, we might decide that the red robot should be prioritized, right? And if we prioritize the red robot, then we can see that as we expand or unroll the space-time graphs for these 2 robots, we can see how these space-time plans no longer collide, right? So if you look at the graph on the right-hand side, you can clearly see which robot is the robot that is moving from the get-go, right? That's the red robot, because in time, its trajectory doesn't stay over the same XY position. Whereas the blue robot stays static until a given time and only then starts moving. And the point at which the blue robot starts moving is the point at which it has clearance to use the width of the corridor it needs to move through, right? And so we can solve these kinds of problems by representing them with this kind of structure in space-time to then understand how to coordinate multiple robots' plans within one given abstraction, right? So you're now thinking, okay, well, in this scenario, we prioritize the red robot, but would the performance have been similar or even better if I would have prioritized the blue robot? And this is an important question and clearly leads to more or less optimal solutions. And many solutions and methods have been developed to solve this prioritization problem. So the key question that these various works answer is, well, what is the best way to prioritize robots? Now, the best way of doing this is clearly evaluating all n factorial options when we have n robots in a system that can communicate with each other, right? And by solving this, going through all possible prioritizations will tell us, okay, this is the best ordering of the robots, and then you're just going to work with this. Okay, and you can do this either offline or online, depending on the way you're going about the planning task. If you don't want to go through n factorial prioritization options, there are also some heuristics you can use to prioritize. And various heuristics have been proposed, and these various heuristics all have different pros and cons, depending on what kind of applications you're interested in. You might want to use one heuristic over another. So, for example, using ideal path length has as a consequence that robots with longer ideal path lengths get priority, and hence they get to plan first. And so this, you could maybe think that this kind of solution is probably good when you're trying to minimize the make span, right? So the robots that are ready are kind of burdened by their long paths, don't get additionally burdened through some less convenient prioritization orders that would even disadvantage them even more in such systems. We could also consider planning time, where robots that are kind of computing for a longer time tend to get priority in saying, okay, I've been computing for a whole bunch of seconds here, let me go first now so that I don't have to compute everything that I've computed again, right? So this is another heuristic that one can use. Another interesting heuristic is workspace clutter, where robots that see a lot of clutter in their environment say, hey, I'm really restricted in my motions here and my movements. I think I should get priority over you other guys that seem to have lots of free space around you and potentially can find other ways to plan. So kind of quantifying the amount of workspace clutter is one way of going about the prioritization task. And the final bullet point here that I'm noting is actually a piece of research that we produced in my lab, which considers a concept that we refer to as path prospects, which is nothing other than to say we're quantifying the number of solutions that any given robot has to reach its goal, right? So you could think of potentially a heterogeneous multi-robot system where we have very big robots that don't have that many options to get to their end goals, and potentially very nimble small robots that have much more free space available and hence have more different quantifiably higher number of potential path routes to their final destinations. And what we're saying here is that if you prioritize robots with a lesser number of potential path prospects, you're going to be minimizing make span and flow time. Okay? So those are a couple of different heuristics you might consider when you're going about the prioritization problem using a heuristic approach. So here, just to show you an example of what final solutions might look like. So the blue squares here are robots of different sizes. Their start locations are sketched out here. And the lines here are the solutions that were found through a prioritized planning algorithm that took into account their sizes, so the constraints for them to move through the environment, eventually leading them all to their end goals. So here we don't actually represent the time component, but you get a feeling of how the robots plan their paths through this very cluttered environment whilst avoiding other robots' paths. So what we're going to do now is we're going to switch to the second topic I want to talk about, which is planning in the continuous domain. And I want to start off by showing you a movie that motivates the setting for us. So as I play this movie, what you can see happening here is we're looking at a planning problem where we have 4 robots that have designated goal locations. So it's a labeled path planning problem. And what they're doing here is they're basically sharing local information with each other so that they can, whilst they're planning their paths to their end goals, deconflict their path plans and move around each other in a very efficient way so that they reach their end goals without incurring any collisions. So to start off, I want to give you a bit of a reminder of the Minkowski sum, because we'll be using this notion in one of the methods that I'm going to be introducing to you next. So you've seen these slides before. I just want to do a quick recap. So if you remember, the Minkowski sum of A plus B, what it does is it simply adds all the vectors in A to the points in B, essentially dilating the area of B by A, right? And how did we use this for avoiding robot collisions with obstacles? So the intuition that I'd like you to hold on to is the idea that the Minkowski sum allows us to dilate obstacles such that the area outside of the Minkowski sum is safe for us to move a robot's control point into. And the areas that we want to avoid are basically the areas that are covered by the Minkowski sum. Okay? So we're going to use this idea of the Minkowski sum for deconflicting robot paths in the continuous domain. So the first key method I'm going to be talking about in this lecture is the velocity obstacle method. And it is actually a seminal method, been highly repurposed and reused in the years since it was first published. So the gist of this method is basically to answer the question, if I have 2 robots A and B that are translating in space with a certain velocity, will they collide? And the velocity obstacle not only answers this question, but also uses a representation of this collision space to plan around it in an efficient and effective manner. And the key thing is that the velocity obstacle method guarantees collision freeness. So how does it work? So it consists of several steps, and we'll go through these steps individually. So the first step consists of computing the Minkowski sum between 2 robots. So we're representing the robot areas through this green dot and this blue dot. We have robot A and robot B. And the first thing we're going to do is we're going to compute the Minkowski sum of minus A plus B to find out whether or not robot A would collide into robot B, given that robot B would remain static, okay? So minus A plus B basically tells us where robot A with area A is allowed to move into if B would remain static, right? So in other words, the velocity of robot A, so V sub A, is allowed to point anywhere outside of this grayed out cone here, right? And if robot B were to remain static, then we're okay. And then robot A is allowed to do any motion that leads it outside of this cone. But generally, velocity, so robot B is generally not static and V sub B is generally not 0. So we need to take this idea a step further. So in step 2, what we do is we consider that robot B moves, which is generally the case. And so we need to translate the velocity obstacle of B to A by robot B's speed vector. Okay? Now, given a vector V sub A, we can now analyze if A will crash into B, given that we know VA and VB. And given that, we assume that none of these speeds change, right? So both of these robots know each other's speeds, and these speeds won't be changing. Hence, we know that what robot A needs to do is simply direct its speed outside of this dark gray cone here, right? So if VA is outside of this velocity obstacle, then we know that the robots will never collide, given the assumptions that I listed before. And just for completeness here, I'd like to show you a simple equivalence that basically says that if V of A lies in the velocity obstacle of B to A, then the relative velocity VA minus VB lies in the velocity obstacle of B to A, assuming that B does not move. Okay, so this is a practical equivalence to be aware of. Right, so at this point, we now know where we are not allowed to move into, right? We know where VA is not allowed to control its velocity into, as represented by the velocity obstacle I showed you previously. But how do we use that representation to now plan, right? What we want to do is we want to plan a collision-free path given that we have this information. So what we're going to do now is we're going to assume that we know how the robot is allowed to move, right? So assume we have a motion model for robot A. Then the premise here is that we can compute a set of admissible accelerations for robot A. And the key idea that we're going to exploit now is to say that we're now going to search over all feasible motions for robot A. And we're going to apply this acceleration, so any one of these feasible accelerations given the motion model for a given duration delta t, such that we basically get this abstraction here. If we look at the gray zone that I've illustrated in this panel, that tells us how x dot dot, which is the acceleration, times delta t, gives us the areas within which our new potential or candidate velocity vectors will be pointing, right? So now, given that we know the feasible accelerations, we can compute a set of feasible new candidate velocity vectors. So all that is now left to do is to basically cross-check this new candidate zone with the velocity obstacle that we computed in the previous step, right? And we now, all we need to do is to select a convenient velocity direction that is outside of the velocity obstacle and inside the zone or the area of feasible velocity vectors for robot A. And with that, we've basically solved the problem. So robot A now knows which direction it has to select or which velocity it has to, which control it has to exert in order to avoid a collision and at the same time remain within its feasible motion constraints. So this is the velocity obstacle method. So just to summarize, there are two key assumptions that the velocity obstacle method makes. The first one is that robots need to share their current position and velocity, and we're assuming that they're noise-free. And we're also assuming that the robots will truthfully execute these reported velocities so that they don't change them, right, until the plans have been made and executed, right? So there's one key complication that I want to point out here. And this complication, it has as a consequence that our robots might actually oscillate between decisions on which velocities they will be following. Now, how does this occur? So the scenario in which this occurs is as follows. So assume we have robots with current velocities VA and VB, and they currently lie in each other's velocity obstacles, right? So both robots are now going to select a new velocity v prime A and v prime B, such that both of these new velocities lie outside of the respective velocity obstacles. Okay? So this is exactly what I've taught you to do thus far. But now in this new situation, the old velocities that we previously had, v sub A and v sub B, are potentially legitimate again because they potentially lie outside the velocity obstacles. Now, if VA and VB are preferable in the sense that they're actually more efficient than V prime A and V prime B, then what the robots are going to do is that at the next time step, they're going to choose those velocities again, because actually those are the velocities they want to select in the first place because they're leading the robots on the most direct path to their designated goal locations. And this has as a result that the robots are going to start oscillating between starting maneuvers around each other to actually pointing back into directions that lead them to collision courses. And so in order to get around this oscillatory issue, a new method or an extension to the basic velocity obstacle method was proposed, and this new method is called the reciprocal velocity obstacle method. So the idea here is to, instead of compute a simple velocity obstacle, we'll compute a new type of velocity obstacle that is called the reciprocal velocity obstacle. And this RVO, what distinguishes it from the velocity obstacle is that it has its apex at the average of the velocity vectors of robot A and B. So the basic idea is actually pretty simple. For the robots, instead of now choosing a new velocity for each agent that is outside the other agent's velocity obstacle, the robots are now going to choose a new velocity that is the average of its current velocity and the velocity that lies outside the other agent's velocity obstacle. So without going into further detail on the proof, this method does actually avoid collisions, and the proof is detailed in the paper itself. And they show that by choosing the closest velocity outside this RVO for both agents A and B, the reciprocal velocity obstacles stay exactly in the same position. So now let's have a look at a couple of movies that illustrate the method. So on the left-hand side, you see a simulation of agents that swap positions in a circle. And on the right-hand side, you see a similar scenario where robots swap positions. This scenario was filmed with real robots. And so you'll see that we can effectively use the RVO method to generate efficient trajectories, in the sense that they make very small detours that are guaranteed to be collision-free if we know that the robots can communicate their velocities to each other and compute their reciprocal velocity obstacles as a function of that information. So now I'm going to move on to the final topic of this lecture, which is all about the problem of concurrent assignment and planning of trajectories. So what's new about this problem formulation is that we're actually now considering unlabeled goal locations, where the labels are going to be assigned as part of the optimization problem so that it's convenient for the path planning problem. So more formally, we're going to assume that we have a system of n robots. Each robot needs to reach one of n goals. This is not predefined a priori. And this assignment and the resulting trajectories have to be as efficient as possible with respect to some optimization objective. And the only requirement that we're going to be making is that the resulting trajectories are to be collision-free. And as I mentioned, at the outset of the problem, we don't know which robots are assigned to which goal locations. And that is something that the optimization algorithm will provide us with. So what I'm going to show you that is a result of one of the algorithms that was developed to solve this problem is that we can solve this very elegantly by simply assuming that robots have a minimum separation distance between each other at their start locations as well as the goal locations. And in order to make this specific problem expose a little bit more conducive to understanding, we're going to be assuming that robots are holonomic and that they all arrive simultaneously at their goals. Okay. So just a small animation, what are we actually trying to do here? Well, let's assume we have these 4 black robots and we have 4 locations or destinations we want them to reach. And we want to find out who goes where and how do the robots have to get there. And so we're hoping to find an algorithm that can generate these assignments as well as the trajectories that lead the robots there. So the key question we start out with is, what is a useful optimization objective to consider for this type of problem? So what kind of objective will, if we then solve it, if we optimize it, will lead to this kind of behavior we're hoping to deduce from the solution? So in order to explain what I'm showing you in this panel, I'd just like you first think of the small analogy I'm going to make here. So we're looking at 2 options in this particular slide here for optimization objectives. One is a sum of distances, and one is a sum of distances squared. And before explaining the actual illustrations there, I want you to think of the example where you're looking at a bookshelf where you have a row of books there. And what you want is to move that block of books. You want it to move by one notch to the left, say. And so you have two different ways of actually achieving that, right? You can take the book which is at the rightmost end of that row of books, and you can take it and you can simply put it on the left-hand side of that contiguous block of books. And the other option you have to take to make that shift is to simply I gave it away, is simply to shift the whole contiguous block of books without actually lifting any of the books and moving it across, just shifting all of them one over, okay? So both of these solutions end up in the block of books moving one over to the other end, okay? So what is actually happening under the hood there with those two different solutions is that one of them actually is optimizing the sum of distances, and the other one is actually optimizing the sum of distances squared. So the case where we're actually shifting all of the books one over is optimizing the sum of distances square, as this is a strictly convex cost function. And if we go for the version of sum of distances, that's where we end up taking the book from one end and leaving the other books placed on their locations, and just replacing that one book onto the other end of the contiguous block of books. And so that is now analogous with the situation that we're looking at for robots. So if we look at two robots, a green robot and a blue robot, and we want to find assignments that minimize the sum of distances to the two possible goal locations, right? So here we don't know which robots go to which goals, but it will emerge as a solution of the optimization problem. We'll see that at halftime with the objective of minimizing the sum of distances, these two robots actually collide, right? Because the optimal solution here is to assign the green robot to the top goal and the blue robot to the bottom goal. Now, if we were to optimize the assignment by considering the sum of distances squared, the resulting assignment actually sends the green robot to the bottom goal and the blue robot to the top goal. And if we look at how this pans out over time, at halftime, the robots are not colliding anymore, right? So you can see here that simply by considering two different optimization objectives, we have different behaviors as a function of time. One behavior leads to a collision at halftime, and the other behavior does not lead to collision or is collision-free. So this can actually be proven. So if we consider sum of distances squared and we have holonomic point robots, we can actually generate assignments that are collision-free. And we're going to exploit that in this setup here to solve the concurrent assignment and planning of trajectories problem. So for the case of homogeneous multi-robot systems composed of holonomic robots, we can formulate the problem as follows. So in the first instance, what we want our assignment and the resulting trajectories to be optimal. So we pose the optimization problem, which finds an assignment phi and a set of trajectories gamma such that our cost is minimized. Where here, our cost is simply represented by the sum of distances traveled squared, right? Similar to what I just described to you previously. And it turns out that in this case, if the start locations and the goal locations are separated by a distance delta that is larger than 2 times the square root of 2 times the robot radius, then we can actually guarantee that the trajectories that result from this optimization will be collision-free. So now, because we're considering a cost that is a sum of distances squared, this can now be posed as a linear sum assignment problem. And as you already know, we can solve these problems with the Hungarian algorithm. And what happens is that we actually end up with a very elegant solution, because all we need to do is actually solve the optimization problem I'm posing in the bottom, so the second optimization problem. Because we're basically going to be inferring assignments of robots to goals. We know that we have this constraint on the minimum separation distance of starts and goals. And then since they're holonomic and we know that we're requiring all robots to achieve or reach their goals at the same time, all we need to do is press play, and the trajectories need no more planning other than knowing that we have holonomic robots that arrive simultaneously at their goals. So it's a very simple problem to solve, given this current setup. Now, obviously, there are a couple of challenges, and one of the big challenges here is that we're assuming that our robots are holonomic, so they don't have any turning constraints, for example. And of course, this becomes problematic if we're trying to solve these concurrent assignment and planning problems with actual vehicles that are potentially motion constrained. Nevertheless, we can actually use this assumption of holonomicity and relax it by, for example, creating bounding boxes. And there are a couple of practical tricks we can employ. And what I want to do next, before I conclude this lecture, is just show you a movie to convince you of how we can use this concurrent assignment and trajectory planning method in real-world scenarios. So this is actually using the concurrent assignment and planning of trajectories problem method in motion, right? So what we have here is two platoons of vehicles. We have surrounded by the red rectangle, we have a slow platoon of two vehicles, and surrounded by the green rectangle, we have a faster moving platoon of vehicles. And what we want to do is, well, the fast-moving platoon wants to overtake the slow-moving platoon. And in order to do that, both platoons have to reconfigure their formations. And so we can basically just think of this as an assignment problem, or a concurrent assignment and trajectory planning problem, where robots know that they have to take up new goal positions. We don't necessarily know which robot has to go where, but we know that the formation change has to take a given shape, right? In the case of the red robot group, it has to be on the right-hand side of this highway, and in the case of the green robot group, it has to take positions on the left-hand side of this highway. And then all that remains to be done is to compute these assignments and hit play, and the robots should execute those dedicated trajectories. So let's have a look at how this looks in action. So the green platoon is coming from behind, the red robot platoon reconfigures, they overtake, and then they reconfigure to their preferred formations. And so this is just an example of the kinds of things that we can do with motion planning algorithms that combine assignment for real-world problems. So to conclude, I'd like to just point out a couple of further pointers that I invite you to look at if you're interested to dive into this domain a little deeper. So as usual, we have some seminal papers and also a very good book on planning, the same one as I mentioned in the lecture on single robot path planning. And I'm also listing a couple of more recent papers that describe some of the other methods I talked about today. And the very last bullet point here is something we didn't specifically address in this lecture because it's based on machine learning methods, but I really invite you to have a look at it because it's cutting state-of-the-art research showing how you can actually exploit machine learning techniques to learn communication patterns that can solve NP-hard problems for you in effective manners. And in this particular case, we're looking at the multi-robot path planning problem. So I hope you enjoy these pointers here. It was a pleasure talking to you today in this lecture, and I look forward to speaking to you in the next one.